Network Working Group Request for Comments 1951, Category Informational. P. Deutsch, Aladdin Enterprises, May 1996. Deflate Compressed Data Format Specification version 1.3. Status of this memo. This memo provides information for the Internet community. This memo does not specify an Internet standard of any kind. Distribution of this memo is unlimited. IESG note. The IESG takes no position on the validity of any intellectual property rights statements contained in this document. Notice. Copyright 1996 L. Peter Deutsch. Permission is granted to copy and distribute this document for any purpose and without charge, including translations into other languages and incorporation into compilations, provided that the copyright notice and this notice are preserved, and that any substantive changes or deletions from the original are clearly marked. A pointer to the latest version of this and related documentation in HTML format can be found at the URL ftp://ftp.uu.net/graphics/png/documents/zlib/zdoc-index.html. Abstract. This specification defines a lossless compressed data format that compresses data using a combination of the LZ77 algorithm and Huffman coding, with efficiency comparable to the best currently available general-purpose compression methods. The data can be produced or consumed even for arbitrarily long sequentially presented input data stream using only an a priori bounded amount of intermediate storage. The format can be implemented readily in a manner not covered by patents. Table of Contents. 1. Introduction. 1.1 Purpose. 1.2 Intended Audience. 1.3 Scope. 1.4 Compliance. 1.5 Definition of terms and conventions used. 1.6 Changes from previous versions. 2. Compressed Representations Overview. 3. Detailed Specification. 3.1 Overall Conventions. 3.1.1 Packing into Bytes. 3.2 Compressed Block Format. 3.2.1 Synopsis of Prefix and Huffman Coding. 3.2.2 Use of Huffman Coding in the deflate format. 3.2.3 Details of Block Format. 3.2.4 Non-compressed blocks B-type 00, 3.2.5 compressed blocks length and distance codes, 3.2.6 compression with fixed Huffman codes B-type 01, 3.2.7 compression with dynamic Huffman codes B-type 10, 3.3 compliance, 4 compression algorithm details, 5 references, 6 security considerations, 7 source code, 8 acknowledgements, 9 author's address. 1. Introduction. 1.1 Purpose. The purpose of this specification is to define a lossless compressed data format that is independent of CPU type, operating system, file system, and character set, and hence can be used for interchange. Can be produced or consumed even for an arbitrarily long sequentially presented input data stream using only an a priori bounded amount of intermediate storage, and hence can be used in data communications or similar structures such as Unix filters. Compresses data with efficiency comparable to the best currently available general-purpose compression methods, and in particular, considerably better than the compress program. Can be implemented readily in a manner not covered by patents, and hence can be practiced freely. Is compatible with the file format produced by the current widely used gzip utility, in that conforming decompressors will be able to read data produced by the existing gzip compressor. The data format defined by this specification does not attempt to allow random access to compressed data, compress specialized data, e.g. raster graphics, as well as the best currently available specialized programs. A simple counting argument shows that no lossless compression algorithm can compress every possible input dataset. For the format defined here, the worst-case expansion is 5 bytes per 32K byte block, i.e. a size increase of 0.015% for large datasets. English text usually compresses by a factor of 2.5 to 3. Executable files usually compress somewhat less. Graphical data, such as raster images, may compress much more. 1.2 Intended Audience. This specification is intended for use by implementers of software to compress data into deflate format and/or decompress data from deflate format. The text of this specification assumes a basic background in programming at the level of bits and other primitive data representations. Familiarity with the technique of Huffman coding is helpful, but not required. 1.3. Scope. The specification specifies a method for representing a sequence of bytes as a usually shorter sequence of bits and a method for packing the later bit sequence into bytes. 1.4. Compliance. Unless otherwise indicated below, a compliant decompressor must be able to accept and decompress any dataset that conforms to all the specifications presented here. A compliant compressor must produce datasets that conform to all the specifications presented here. 1.5. Definitions of terms and conventions used. Byte. 8 bits stored or transmitted as a unit, same as an octet. For the specification, a byte is exactly 8 bits, even on machines which store a character on a number of bits different from 8. See below for the numbering of bits within a byte. String, a sequence of arbitrary bytes. 1.6. Changes from previous versions. There have been no technical changes to the deflate format since version 1.1 of the specification. In version 1.2, some terminology was changed. Version 1.3 is a conversion of the specification to RFC style. Compressed representation overview. A compressed dataset consists of a series of blocks corresponding to successive blocks of input data. The block sizes are arbitrary, except that non-compressible blocks are limited to 65535 bytes. That's 65,535 bytes. In other words, 0xFFFF. Each block is compressed using a combination of the LZ77 algorithm and Huffman coding. The Huffman trees for each block are independent of those for previous or subsequent blocks. The LZ77 algorithm may use a reference to a duplicated string occurring in a previous block up to 32K input bytes before. Each block consists of 2 parts, a pair of Huffman code trees that describe the representation of the compressed data part, and a compressed data part. The Huffman trees themselves are compressed using Huffman coding. The compressed data consists of a series of elements of 2 types: literal bytes, of strings that have not been detected as duplicated within the previous 32K input bytes, and pointers to duplicated strings where a pointer is represented as a pair length, comma, backwards distance. The representation used in the deflate format limits distances to 32K bytes and lengths up to 258 bytes, but does not limit the size of a block except for uncompressible blocks, which are limited as noted above. Each type of value, literals, distances, and lengths, in the compressed data is represented using a Huffman code, using one code tree for literals and lengths, and a separate code tree for distances. The code trees for each block appear in a compact form just before the compressed data for that block. 3. Detailed specification. 3.1. Overall conventions in the diagrams below. A box like this, diagram, the vertical bars might be missing, represents 1 byte. A box like this, diagram, represents a variable number of bytes. Basically, an ASCII box, if it's drawn with dashes on the top and bottom edges, that means a single byte. And usually within that diagram, from what I'm seeing, is it will show the individual bits within that byte. A ASCII box that is drawn with equal signs on the top and bottom edges, that will represent 1 byte, so I'm guessing within the diagrams it will list the byte values rather than the bit values. Bytes stored with a computer do not have a bit order, since they are always treated as a unit. However, a byte considered as an integer between 0 and 255 does have a most and least significant bit, and since we write numbers with the most significant digit on the left, we also write bytes with the most significant bit on the left. In the diagrams below, we number the bits of a byte so that bit 0 is the least significant bit, i.e. bits are numbered, and within this diagram we have 0, 1, 2, 3, 4, 5, 6, and 7, and those are the bit indexes of the individual binary values within a byte. And when I am saying 0, 1, 2, 3, 4, 5, 6, 7, that is from right to left, because the most significant bit is going to be on our left and the least significant bit is going to be on the right, just like we write normal base 10 numbers. And this is within a rectilinear diagram that has minus symbols on the top and bottom edges of this ASCII box. Within a computer, a number may occupy multiple bytes. All multi-byte numbers in the format described here are stored with the least significant byte first at lower memory address. For example, the decimal number 520 is stored as, and we have two boxes labeled 0 and 1 on the top edge. Within the first box, we have 4 zeros, a 1, and then 3 zeros. Within the second box, labeled 1, we have 6 zeros, a 1, and then 1 0. The first box, labeled 0, has a comment on it that says less significant byte equals 8. The second box has a label on it that says more significant byte equals 2 times 256, right? Because we're bit shifting over 8 to the left. So this is, wait, hold on. More significant byte, yes, that's correct. So while I'm saying that the second box is shifted over to the left 8 bits, that is because once we create the actual number from this array of bytes, the second entry is going to need to be the one that's going to get shifted over when we are bit packing these two array entries together, which is kind of confusing. I don't know why they decided to do it in this flip-floppy kind of order. So basically, when you're reading the data from an array, the first byte here will not be shifted when you're bit packing it together, and the second byte needs to be shifted over 8 bits to the left so that you can pack together those 2 bytes to create the full number that is 2 bytes long. 3.1.1 Packing into bytes. This document does not address the issue of the order in which bits of a byte are transmitted on a bit sequential medium, since the final data format described here is byte rather than bit-oriented. However, we describe the compressed block format in below as a sequence of data elements of various bit lengths, not a sequence of bytes. We must therefore specify how to pack these data elements into bytes to form the final compressed byte sequence. Data elements are packed into bytes in order of increasing bit number within the byte, i.e. starting with the least significant bit of the byte. Data elements other than Huffman codes are packed starting with the least significant bit of the data element. Huffman codes are packed starting with the most significant bit of the code. In other words, if one were to print out the compressed data as a sequence of bytes starting with the first byte at the right margin and proceeding to the left with the most significant bit of each byte on the left as usual, one would be able to parse the result from right to left with fixed width elements in the correct MSB to LSB order and Huffman codes in the bit reversed order, i.e. with the first bit of the code in the relative LSB position. Or in my words, if you read it like a Japanese person from right to left, then you would be able to correctly interpret the data stream. Aside, a priori, relating to or denoting reasoning or knowledge which proceeds from theoretical deduction rather than from observation or experience. For example, if we want to know how many unique values are in 2 bytes, we could say, well, 1 byte is 0 to FF, which is 0 to 255, and that's 256 unique values. And if we were to double that, because we have 2 bytes, then we would have 256 times 2, which is 512. Remember that 0 is a value, therefore that is 0 to 511, but either way we have 512 unique values, and that is an a priori deduction. 3.2 Compressed block format. 3.2.1 Synopsis of prefix and Huffman coding. Prefix coding represents symbols from an a priori known alphabet by bit sequences, codes, one code for each symbol in a manner such that different symbols may be represented by bit sequences of different lengths, but a parser can always parse an encoded string unambiguously, symbol by symbol. Aside, when they say string in the documentation, they mean an array of char. An array of char just means an array of bytes, because char is 8 bits. ASCII is 7 bits, so we're using the best fit. String in this documentation does not actually mean human-readable ASCII letters. It means bytes. It's better to think of string as a sequence of bytes, not a sequence of letters, because we are not encoding text data here. I'm actually reading this to understand PNG format better. So for example, if you look at the C library memcopy function, you'll notice that to get memcopy, you're going to include something called string.h. Therefore, when you're thinking about strings, you want to think sequence of bytes, not ASCII letters. If you think ASCII letters when you're reading this documentation and you see string, you're going to be highly confused. We define a prefix code in terms of a binary tree in which the two edges descending from each non-leaf node are labeled 0 and 1, in which leaf nodes correspond one for one with are labeled with the symbol of the alphabet. Then the code for a symbol is the sequence of zeros and ones on the edges leading from the root to the leaf labeled with that symbol. For example, aside, that previous paragraph made absolutely no sense to me. I've read it multiple times, and I've also done some tutorials on Huffman encoding, so I understand what they're saying, but for whatever reason, the paragraph just seems like complete gibberish to me. So I've taken their diagram here, and I've rewritten it. So theirs is the top diagram, and my rewrite is this diagram. So they conceptualize the same exact thing, but I believe my diagram is going to make this easier to understand. Basically, we want to record the decisions we took to get to the terminal node that contains a letter. For example, D right here is 0, 1, 0, and that would be left, right, left, encoded in binary. So we'll start at the top of the tree here, and we have a piece of paper, and we're wandering through the woods, and we decide we want to go left. So we'll end up here at this next fork in the road. We'll write down a 0 on our piece of paper because we just went left. We're at another fork in the road, and we got to go, do we want to go right or left? We decide, okay, we'll go right. So we're going to write down a 1 on our piece of paper. We're at another fork in the road. We got to decide, do we want to go right or left? We decide to go left, so we put a 0 down on our piece of paper. And then we realize there's a D right in front of us, not a fork in the road, so we're at D. And the decisions we took were left, right, left, and that is the binary to get to D. Now, the reason I drew it like this is because it's more easy to conceptualize a starting point, first of all. And also, if we have a data structure, it just makes more sense. So here's my Huff node data structure. And if we're at a fork in the road, we have a left and right decision we can make, which are going to be pointers to another node. And if we are at a terminal node, we will have a letter. But it's either one or the other. So either this data exists or this data exists, but not both at the same time. So I just feel like this just makes more sense to me. So let's try to get to C and then see if the chart actually agrees with us. So we're at a fork in the road in the woods, and we decide to go left, right, and right. And that is 0, 1, and 1. 0, 1, and 1, and that is C according to their table. And remember that this is actual binary. A parser can decode the next symbol from an encoded input stream by walking down the tree from the root at each step, choosing the edge corresponding to the next input bit. Given an alphabet with known symbol frequencies, the Huffman algorithm allows the construction of an optimal prefix code, one which represents strings with those symbol frequencies using the fewest bits of any possible prefix codes for that alphabet. Such a code is called a Huffman code. See reference 1 in Chapter 5, references for additional information on Huffman codes. Note that in deflate format, the Huffman codes for the various alphabets must not exceed certain maximum code lengths. This constraint complicates the algorithm for computing code lengths from symbol frequencies. Again, see Chapter 5, references for details. 3.2.2 Use of Huffman coding in the deflate format. The Huffman codes used for each alphabet in the deflate format have two additional rules. Star. All codes of a given bit length have lexicographically consecutive values in the same order as the symbols they represent. Star. Shorter codes lexicographically precede longer codes. Aside. Those two extra constraints on our Huffman codes are because we will be using canonical Huffman codes. Canonical Huffman codes are Huffman codes with some strict ordering constraints, which makes it possible to omit the Huffman code table or the Huffman tree from your encoded data and still be able to decode the data. Normally, when you encode something using Huffman codes, you need to store the tree alongside the encoded data. But if you use canonical Huffman codes, the only thing you need to store alongside the compressed data is a list of these symbols and the frequency, the number of times, that symbol occurs. And with just a table of the symbol and the frequency, you can reconstruct all of the Huffman codes. The first thing you need to do is you need to sort everything. So you'll have groups sorted by frequency, and then within each group, you can sort lexicographically. If it was ASCII data, then you could just sort within the group alphabetically. And that'll give you a strict ordering constraint on all of your symbols. And then once you have all your symbols sorted by frequency, we can use this algorithm here. And we will fill out a table and then generate our Huffman codes. So right here, BL count is bit length count. So this is saying we have Huffman codes that only have 1 bit in them. How many do we have? We have 1. How many Huffman codes that have 2 bits? We have 1. So basically, your high frequency codes, right? Those are going to get the smaller codes, and then your low frequency codes, the things that aren't showing up as much, those need to get codes with more bits. So sorry, let me say that again. High frequency symbols get shorter sequences, and then low frequency symbols get higher frequencies, right? And that's the essence of how you're going to compress that data. The things that occur more often get smaller sequences. So the bit length here is the amount of bits in your Huffman code. And so the smaller bit length ones are going to be your high frequency symbols. And then your larger bit length codes are going to be your low frequency symbols. So how you fill out this data will depend on your unique frequencies for the different symbols that you're encoding. And once you've filled out this table here, right here, then you can run this algorithm right down here, and it is going to give you the first Huffman code of each length. And then to get the next code of a certain length, you just count up as you would count with normal integers, right? But they're binary codes, but the next binary code is just counting in binary to the next number. An example printout of this is right here. So I've just ran it, and this is an example of what the different codes will look like for the current data set. This one is going to be ignored right here because we don't have any codes of 0 bits. And for the first code that has a length of... I might have that wrong, because this might be a length of 2. No, this is... bits 2. No, this is 2 bits. Okay, so I think I may have the wrong offset on here. But the idea is that for different codes of different binary lengths. These are going to be the first codes of these different binary lengths. So let's go back over to here. And it is, to get to this algorithm that I reconstructed in JavaScript, you're going to want to go to www.w3.org/graphics/png/rfc1951, and it's in section 3.2.2, use of Huffman coding in the deflate format. So that's, I'm done with that aside there. Not the best explanation. All I really want you to understand from this aside is the reason we use these extra constraints is because we're using canonical Huffman codes. Okay, so the first thing I want you to know is canonical Huffman codes. The second thing I want you to know is canonical Huffman codes make it so that we do not have to encode the entire Huffman tree along with the compressed data. We could recode the example above to follow this rule as follows, assuming that the order of the alphabet is A, B, C, D. Symbol and code table. For these symbols, they are ordered A, B, C, D, of course. And the codes are 10, 0, 110, 111. And that is the diagram we're seeing here. I.e., 0 precedes 10, which precedes 11x, comma, and 110 and 111 are lexigraphically consecutive. So lexigraphically, I think, is a more encompassing term than alphabetically, if I understand correctly. I could be wrong. Given this rule, we can define the Huffman code for an alphabet just by giving the bit lengths of the codes for each symbol of the alphabet in order. This is sufficient to determine the actual codes. In our example, the code is completely defined by the sequence of bit lengths 2, 1, 3, 3. The following algorithm generates the codes as integers intended to be read from most to least significant bit. The code lengths are initially in tree_i.len. The codes are produced in tree_i.code. 1. Count the number of codes for each code length. Let BL count within square brackets n be the number of codes of length n, where n is greater than or equal to 1, because we cannot have a code of length 0 bits. 2. Find the numerical value of the smallest code for each code length. Code equals 0. BL count within square brackets equals 0. For bits equals 1 to max bits inclusive. And then a recursive, well, not recursive, an iterative formula. Code equals code plus BL count within square brackets bits minus 1. And then all shifted over to the left 1, right? And that will grow our code by 1 bit long for each iteration of this loop. Once we've generated the code, we're going to put it into our lookup table. So next code within square brackets bits, that's our key, equals the actual Huffman code. 3. Assign numerical values to all codes using consecutive values for all codes of the same length with the base values determined at step 2. Codes that are never used, which have a bit length of 0, must not be assigned a value. For n equals 0 to max code inclusive, I'm not sure why that's an inclusive loop, because I was thinking, well, if you have the codes for the alphabet, because you're encoding text and all of the letters of the alphabet are used, that would be 0 to 25, because that would include all letters of the alphabet. I'm guessing the reason we are starting at 0 has something to do with how the formula above, or the algorithm above, is excluding the first index. That's just a guess, though. I don't know why. So anyways, for n equals 0 to max code inclusive, len equals tree within square brackets n dot len. If len not equal to 0, tree within square brackets n dot code equals next code within square brackets len. And then once we've assigned that code is no longer valid because we've already used it. So we're going to take that next code entry and do a plus plus on it. And that's going to change the code that is stored, the Huffman code that is stored for that code length. And it's just going to increment it by 1. And that way, the next time we go to fetch out a code of that given length, we'll get another unique code out of it. Example, consider the alphabet A, B, C, D, E, F, G, H with bit lengths 3, 3, 3, 3, 3, 2, 4, 4. After step 1, we have N with 2, 3, and 4, BL count within square brackets N, 1, 5, and 2. So our rows are 2, 1, 3, 5, and 4, 2. Step 2 computes the following next code values. Our N column has 1, 2, 3, and 4. Our next underscore code within square brackets N column has 0, 0, 2, 14. Step 3 produces the following code values. Symbol, length, and code columns. The symbol column has A, B, C, D, E, F, G, H. The length column has 3, 3, 3, 3, 3, 2, 4, 4. And the codes are 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 0, 0, 1, 1, 1, 0, and then all ones. I'll say that again, but this time I'll go in row order. So the columns for each row are symbol, length, and code. A, 3, 0, 1, 0. B, 3, 0, 1, 1. C, 3, 1, 0, 0. D, 3, 1, 0, 1. E, 3, 1, 1, 0. F, 2, 0, 0. G, 4, 1, 1, 1, 0. H, 4, all ones, and those are 4 ones. As far as understanding what the hell that means, I am going to guess you can't really, unless you have a very good photographic memory. Yeah, I'd have to look at these tables side by side with that pseudocode to understand what the relationships here are. But let's just keep on going. 3.2.3 Details of block format. Each block of compressed data begins with 3 header bits containing the following data. First bit, B final. Next 2 bits, B type. Note that the header bits do not necessarily begin on a byte boundary, since a block does not necessarily occupy an integral number of bytes. That's just saying that the compressed data is compressed binary, right? And the fact that we're packing everything into bytes is just a implementation detail, but we're really just working with a binary stream, and that's why things may not necessarily be on a byte boundary. B final is set if and only if this is the last block of the dataset. B type specifies how the data are compressed as follows. 0, 0, no compression. 0, 1, compressed with fixed Huffman codes. 1, 0, compressed with dynamic Huffman codes. 1, 1, reserved within parentheses, error. So there's only 3 valid combinations because all ones is an error, or possibly reserved for some type of future use, which was never implemented. The only difference between the 2 compressed cases is how the Huffman codes for the literal/length and distance alphabets are defined. In all cases, the decoding algorithm for the actual data is as follows. Do. Read block header from input stream. If stored with no compression, then skip any remaining bits in current partially processed byte. Read len and nlen, see next section. Copy len bytes of data to output. So if stored with no compression, that's what we're doing. If otherwise, so let's simplify that and say if not stored with no compression, and if compressed with dynamic Huffman codes, read a representation of code trees, see subsection below. And we have loop until end of block, code recognized, decode literal/length values from input stream. If value less than 256, copy value literal byte to output stream. Otherwise, if value equals end of block 256, break from loop. Otherwise, value equals 257 to 285, decode distance from input stream. Move backwards distance bytes in the output stream and copy length bytes from this position to the output stream. End loop, while not last block. So let's look at this again. So we have a while and then while not last block. Okay, no, so end loop and while not last block. So there's two loops in here. So the first outer loop is reading block headers and decoding blocks. And then this inner loop here is decoding the actual data within the different blocks. And I believe blocks are the things that have different Huffman trees, right? Because you can only have so many Huffman codes, and I think that somehow limits the block size. I'm not sure. Note that duplicated string references may refer to a string in a previous block, i.e. the backwards distance may cross one or more block boundaries. However, a distance cannot refer past the beginning of the output stream. An application using a preset dictionary might discard part of the output stream. A distance can refer to that part of the output stream anyway. Note also that the referenced string may overlap the current position. For example, if the last two bytes decoded have values x and y, a string reference with tuple length equals 5, distance equals 2, adds xy, xy, x to the output stream. We now specify each compression method in turn. 3.2.4 Non-compressed blocks B-type 00. Any bits of input up to the next byte boundary are ignored. The rest of the block consists of the following information. Diagram. We have two bytes. Well, they're not bytes. It almost looks like... Not sure how to read the diagram because earlier in the documentation they definitely said that boxes that were using these dashes represented the bits within a byte or individual bits. And there's only 2 bits here. And then there's 2 more bits. And this first number is whatever the data is. And then this next number, I believe, is like the one's complement. Some type of like data integrity check thing. So I don't understand why there's only 4 bits here. That doesn't make sense to me. Anyways, let's just read it. Len is the number of data bytes in the block. Nlen is the ones complement of len. 3.2.5 Compressed blocks, length and distance codes. As noted above, encoded data blocks in the deflate format consist of sequences of symbols drawn from 3 conceptually distinct alphabets, either literal bytes from the alphabet of byte values 0 to 255, or length, backwards distance tuple pairs, where the length is drawn from 3 to 258, and I don't know if that is inclusive or not. It must be inclusive because the 0 to 255 would be inclusive because that would be 0 to FF. And distance is drawn from 1 to 32, 768. I think that's the tuple pair, maybe? I don't know. In fact, the literal and length alphabets are merged into a single alphabet, 0 to 285, where the values 0 to 255 represent literal bytes, and the value 256 indicates the end of block. and values 257 to 285 represent the length codes, possibly in conjunction with extra bits following the symbol code as follows. Okay, so that made absolutely no sense to me. I'm just going to read it one more time without pausing in confusion, so that maybe if you understand what the hell is going on, I won't interrupt the train of thought being communicated here. As noted above, encoded data blocks in the deflate format consist of sequences of symbols drawn from three conceptually distinct alphabets, either literal bytes from the alphabet of byte values 0 to 255 inclusive, or a tuple, length, comma, backwards distance pairs, where the length is drawn from inclusive 3 to 258, and the distance is drawn from inclusive 1 to 32, 768. In fact, the literal and length alphabets are merged into a single alphabet, inclusive 0 to 285, where values 0 to 255 represent literal bytes, and values 256 indicate end of block, and values 257 to 285 257 to 285 represent length codes, possibly in conjunction with extra bits following the symbol code as follows. 3 extra tables with 3 columns. Column 1 code, column 2 bits, column 3 lengths. First table, codes. 257, 258, 259, 260, 261, 262, 263, 264, 265, 266. Bits. 0, 0, 0, 0, 0, 0, 0, 0, and 1, and 1. Maybe that means extra bits. It's not actually a table labeled extra. That would make more sense. Lengths, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12, 13, and 14. Next table, code 2267. Okay, so this is just sequentially 267, 268, 269, 270. And so this is, all these codes are going from 257 to 258. And then the amount of bits is slowly increasing from 1 to 5, and then the final 285 is 0. And we have code lengths. Those are also increasing, and eventually we get a length up to 258. Okay, let's just keep going. The extra bits should be interpreted as a machine integer stored with the most significant bit first, e.g. bits 1110 represent the value 14. With the most significant bit first. Okay, so it's kind of like inverted binary codes, because you're going to be reading these backwards. This is not normally how you would read a binary literal. We got more tables. The code, extra bits, dist, and we have it broken up into 3 pieces. I think it's all the same table. It's just been formatted to fit nicely on this page. So the codes are sequentially, well, not quite sequentially, but they're going 1, skipping some, and then eventually go all the way to 29. The distances 1, 2, 3, 4, 5, and 6, 7, and 8. 9 through 12, 13 through 16, 17 through 24, 25 through 32. And then more distances, 33 to 48, 49 to 64, blah, blah, blah. Let's keep going. 3.2.6, compression with fixed Huffman codes, B type equals 0, 1. The Huffman codes for the 2 alphabets are fixed. They are not represented explicitly in the data. The Huffman code lengths for the literal/length alphabet are literal value 0 to 143, bits 8, codes 0, 0, 1, 1, and then 4 zeros through 1, 0, and then 6 zeros. Yeah, because that would make it 8, yeah. 144 to 255 is going to be 9 bits, and then there is a binary sequence for that. 256 through 257 is 7 bits, another binary sequence, and it's a range. 280 to 287, 8 bits, and another binary range. The code lengths are sufficient to generate the actual codes as described above. We show the codes in the table for added clarity. Literal/length values 286 to 287 will never actually occur in the compressed data, but participate in the code construction. Distance codes 0 to 31 are represented by fixed-length 5-bit codes, with possible additional bits as shown in the table, shown in paragraph 3.2.5 above. Note that the distance codes 30 through 31 will never actually occur in the compressed data. 3.2.7 Compression with dynamic Huffman codes. B-type equals 1, 0. The Huffman codes for the two alphabets appear in the block immediately after the header bits and before the actual compressed data. First, the literal/length code, and then the distance code. Each code is defined by a sequence of code lengths as discussed in paragraph 3.2.2 above. For even greater compactness, the code length sequences themselves are compressed using Huffman code. The alphabet for code lengths is as follows. 0 to 15 represents code lengths of 0 to 15. 16. Copy the previous code length 3 to 6 times. The next two bits indicate repeat length. 0 equals 3, 3 equals 6. Example, codes 8, 16, plus 2 bits, 11. 16 plus 2 bits, 10. Will expand to 12 code lengths of 8, 1 plus 6 plus 5. 17. Repeat a code length of 0 for 3 to 10 times. 3 bits of length. 18. Repeat a code of length of 0. Repeat a code length of 0 for 11 to 138 times. 7 bits of length. I'm not sure what they mean by repeat a code length of 0. I guess that means it's a runline sequence that goes 11 to 138 times. I don't know. Let's keep scrolling. A code length of 0 indicates that the corresponding symbol in the literal/length or distance alphabet will not occur in the block and should not participate in the Huffman code construction algorithm given earlier. If only one distance code is used, it is encoded using 1 bit, not 0 bits. In this case, there is a single code length of 1 with 1 unused code. One distance code of 0 bits means that there are no distance codes used at all. The data is all literals. We can now define the format of the block. 5 bits, HLIT. Number of literal/length codes, 257 to 268. 5 bits, HDIST, so HDIST. Number of distance codes, -1. Oh, those were, okay, god damn it. 1 through 37, 4 bits, HClen, number of code lengths codes, -4. I don't know if they're using that to be a minus or if they're using that to be a colon. But we have 4 through 19 for number of length codes. Yeah, I don't know. HClen plus 4 times 3 bits, colon, code lengths for the code length alphabet given just above, in the order 16, 17, 18, 0, 8, 7, 9, 6, 10, 5, 11, 4, 12, 3, 13, 12, 14, 1, 15. I believe this is an array that is hard-coded into puff.c. It looks very familiar. These code lengths are interpreted as 3-bit integers, 0 through 7, as above. A code length of 0 means the corresponding symbol, literal/length, or distance code length, is not used. HLIT plus 257 code lengths for the literal/length alphabet, encoded using the code length Huffman code. HDIST plus 1 code lengths for the distance alphabet encoded using the code length Huffman code. The actual compressed data of the block encoded using the literal/length and distance Huffman codes. The literal/length symbol 256 end of data encoded using the literal/length Huffman code. The code length repeat codes can cross from HLIT plus 257 to the HDIST plus 1 code lengths. In other words, all code lengths form a single sequence of HLIT plus HDIST plus 258 values. 3.3 Compliance. A compressor may limit further the ranges of values specified in the previous section and still be compliant. For example, it may limit the range of backwards pointers to some value smaller than the 32K. Similarly, a compressor may limit the size of blocks so that a compressible block fits in memory. A compliant decompressor must accept the full range of possible values defined in the previous section, and must accept blocks of arbitrary size. Compression algorithm details. While it is the intent of this document to define the deflate compressed data format without reference to any particular compression algorithm, the format is related to the compressed formats produced by LZ77, Lempel-Ziv 1977, see reference 2 below. Since many variations of LZ77 are patented, it is strongly recommended that the implementer of a compressor follow the general algorithm presented here, which is not known to be patented per se. The material in this section is not part of the definition of the specification per se, and a compressor need not follow it in order to be compliant. So basically, if you want to cover your ass legally, you should probably code it the way they're telling you to code it. But this was 1996. I'm sure a lot of patents have expired since then. The compressor terminates a block when it determines that starting a new block with fresh trees would be useful, or when the block size fills up the compressor's block buffer. The compressor uses a chained hash table to find duplicate strings, using a hash function that operates on 3-byte sequences. At any given point during compression, let XYZ be the next 3 input bytes to be examined. Not necessarily all different, of course. First, the compressor examines the hash chain for XYZ. If the chain is empty, the compressor simply writes out X as a literal byte and advances 1 byte in the input. If the hash chain is not empty, indicating that the sequence XYZ, or, if we are unlucky, some other 3 bytes with the same hash function value has occurred recently, the compressor compares all strings on the XYZ hash chain with the actual input data sequence starting at the current point and selects the longest match. The compressor searches the hash chain starting with the most recent strings to favor small distances and thus take advantage of the Huffman encoding. The hash chains are singly linked. There are no deletions from the hash chains. The algorithm simply discards matches that are too old. To avoid a worst-case situation, very long hash chains are arbitrarily truncated at a certain length, determined by a runtime parameter. To improve overall compression, the compressor optimally defers the selection of matches, lazily matching, after a match of length n has been found. The compressor searches for a longer match starting at the next input byte. If it finds a longer match, it truncates the previous match to a length of 1, thus producing a single literal byte, and then emits the longer match. Otherwise, it emits the original match and, as described above, advances n bytes before continuing. Runtime parameters also control this lazy match procedure. If compression ratio is most important, the compressor attempts a complete second match regardless of the length of the first match. In the normal case, if the current match is long enough, the compressor reduces the search for a longer match, thus speeding up the process. If speed is most important, the compressor inserts new strings in the hash table only when no match was found or when the match is not too long. This degrades the compression ratio, but saves time since there are both fewer insertions and fewer searches. References. and this is section 5. 1. Huffman, D.A., a method for construction of minimum redundancy codes, proceeding of the Institute of Radio Engineers, September 1952, volume 40, number 9, pp 1098 through 1101. 2. Ziv J. Lempel A universal algorithm for sequential data compression, IEEE, Transactions on Information Theory, Volume 23, Number 3, pp 337-343. That might mean pages, I don't know. 3. Gailey J-L and Adler M. zlib documentation and sources available in ftp://ftp.uu.net/pub/archiving/zip/doc. 4. Gailey J-L and Adler M. gzip documentation and sources available as gzip-star.tar in ftp://prep.ai.mit.edu/pub/gnu. 5. Schwartz, E.S. and Kalik, B. Generating a canonical prefix encoding, COMM.ACM, 7,3, March 1964, pp 166169. 6. Hirschberg and Luer, efficient decoding for prefix codes, COM ACM 33, 4, April 1990, pp 449 through 459. Not too useful to me there, but for entirety's sake, I just read it. Source code. The source code for a single language implementation of a deflate compliant compressor and decompressor is available within the zlib package at ftp://ftp.uu.net/pub/archiving/zip/zlib. 8. Acknowledgements. Trademarks cited in this documentation are the property of their respective owners. Phil Katz designed the deflate format. Jean-Luc Galli and Mark Adler wrote the related software described in the specification. Glenn Randers Fierson converted this document to RFC and HTML format. Section 9. Author's address. L. Peter Deutsch, Aladdin Enterprises, 203 Santa Margarita Ave, Menlo Park, California, 94025. Phone 415-322-0103, AM only. Fax 415-322-1734. Email ghost@aladdin.com. Questions about the technical content of the specification can be sent to Jean-Luc Galli, gzip@prep.ai.mit.edu, and Mark Adler, Madler at alumni.caltech.edu. Editorial comments on this specification can be sent by email to lpeterdeutsch at ghost@aladdin.com, Glenn Randers Fierson, rand eg at alumni.rpi.edu. And that is all 17 pages of this specification. And I gotta say, I still need to do more learning.